So in this video, I'll show you how to write HDL code to describe ROM, read-only memory. And just as a reminder, an FPGA doesn't actually have any dedicated ROM. It has RAM, which is random access memory. However, we can hack our way around it and we can write some code that will be interpreted by Vivado as either as a combinational circuit or as basically just a bunch of lookup or large lookup tables. Remember, ROM doesn't need a clock, doesn't need anything. You just specify an address, it will give you what's stored in that address. So technically, it is just a lookup table or a combinational circuit. So I'll show you a couple of ways to actually write that particular code to describe ROM. So I'm here in Vivado. I opened a new module. I called it ROM with file, and you'll know why in a minute. And as inputs, as you might anticipate, I really don't need a lot of inputs and a lot of outputs. I only need one input, and that's actually the address I'm trying to read. And I only need one output, and that's the data I'm trying to read. There's no need for write. There's only a read port. So you can think about it as a memory array with read capability only. So let's start by writing the code. The code for it is really simple and straightforward. Well, it's memory, so the first thing we need to do is just specify the memory. And of course, we can call it whatever we want. I'm just going to call it ROM. And we know it's sort of a 2D array. I'm going to have to specify something here and something here. Well, the thing that comes first is usually associated with data, something similar to what we've seen before. And this code is not generic, so you can see that it's a bunch of numbers and you can modify it according to your needs. So this one here is telling me my data is actually 2 bits. It's actually ranging between the least significant bit has an index 0 and the most significant bit has an index 1. And the address is telling me from 0 to 2, so technically it's 3 bits. And we know that it should go from, for a 3-bit, it should go from 0 to 7. It doesn't have to go to 7, but that's the maximum like you can go to. All right, so for example, like if you need only 5 rows, you can specify it that way. But anyway, we're already utilizing this. This is I'm gonna utilize all of them, at least in this particular example. Okay, so we specified the memory. Okay, so what's next? Well, what's next is actually to specify its memory. So we need to do write and read port. But wait a minute, this is ROM, read-only memory. So there's no write port. So all we have to do is just specify the read port. And the read port is actually what we call data. And we said, well, it is ROM at exactly the address. And we're done. That describes ROM. All right. But you might be asking yourself, okay, well, this is silly, it's silly and simple, but then what's the point of it? Well, if I can't write into it, I need to store some data into it. And the solution is really interesting. So here's how we can do it, at least in Vivado. So Vivado allows you to initialize a memory, actually any of the memories we've seen so far, you can initialize it with certain data. And how do we initialize it? Well, we're going to use initial. It's a construct that is usually associated with simulation only. So if you use initial in any of the code we've seen throughout this particular course, it technically, when you put it on the FPGA, this initial will be kind of ignored. So let's assume they initialize some sort of a signal to 0 or 1. It really doesn't matter whenever you put it on the FPGA, whenever you synthesize it. But it will matter whenever you deal with simulations or test benches. However, if we're dealing with ROM or actually memory, that story changes a little bit. And as it turns out, that this initial actually will be will help me preload any memory with some sort of a data initially, because whenever you're programming the FPGA, you actually can load that data along with the program. All right, so let me show you then, and let's continue. So how do I start? Well, initial, because I only need to do it once at the very beginning, but I don't need an always, I just need it once. And what we're going to be doing is we're going to use a system function. And as you might recall, a system function kind of like stop and a couple of others that we've seen throughout the semester start with a $sign. And then this one here is, it's telling me read memory. Okay, and then you're going to have to specify the file that you want to read. Is it binary or is it hex? And you can see that the color is changing because that's a known system function. And then we're going to do this here. So I'm going to do it with binary. So I'm going to use read memory binary, and then I'm going to tell it, well, the name of the file is going to be truth table, for example, .mem. Okay, and then I want you to read that file and store it in the memory ROM. Why do I have to specify that? Because I might have like different memory or different 2D arrays, if you can think about it that way, and you can initialize it separately. Also, please note that you can actually parameterize this. If for some reason or another you want to like create some sort of a generic Chrome, you can actually parameterize the file name. But anyway, let's go ahead and just fill out that file with some data that I initially want to write into that particular ROM. And that's why I called it ROM with file, because we're loading it with a file. So we're going to have to go to sources, and we're going to have to add, okay, and then from sources we're going to do add or create design source, and then from here you go and you say, well, I want to create a file, and now you're going to have to go to file type, and now instead of Verilog, a Verilog header or VHDL, you're going to go and say memory file, and then you can say, well, I need something called truth table, and then you can click OK, and it's telling me, well, you have a file name that way. And really I created it, and you can see it in here because I created it already. You can see that I have something called a memory file under the design sources. If I double click on it, I'll see it. When you start at the very beginning, it will be empty, but I went ahead to save some time and I just throw the data I want into it. So let me just make this a little bit bigger so we can see it in here. So just to tell you what I did in here. So my data is 2-bit, and I have 8 of these data because 2 to the power 3 is 8. Okay, so taking a look at this memory, you can see that each row has data, and this data is 2-bit. This is why you have 1, 0, 0, 0, and so forth. And because I have the address is 3 bits, I have between line 1 all the way to line 8. And now this data will be loaded to this ROM, and now whenever you put some sort of an address in here, let's assume you put the address 5, you can see that that will be, I believe it's here because this is 0, 1, 2, 3, 4, 5. It's actually that one in here. Remember, it's like a start with 0. This line number should start with 0. Anyway, you get the idea. That actually loads it, or loads that particular memory with that particular value. Now again, before we actually go and put the the Rtl analysis and the implementation, just to show you that what type of resources we're using, I just want to emphasize that you can actually write the same exact file with hex. All you have to do is just change this to an H and then convert all these numbers to hex. For example, this would be, I believe, a 2, this would be a 0, this will be a 3, and so forth. I wrote a 4, but it's a 3. Now let's take a look at the schematics for this file. And as I expected, it actually Vivado figured out that I'm writing read-only memory, and it's just implementing it with an Rtl ROM. It's actually, you get the address, you get the data. It's interpreted because I'm not writing anything into it. I don't have a write port. And taking a look at the utilization report after running the implementation, it tells me that you are using one lookup table, no flip-flops needed, and no BRAM and no distributed RAM. Let's just think about it for a second. Why is it doing that? Well, it's actually obvious from here. Remember, an Arctic 7 device that we're using, which is specified in this project, it has lookup tables with 6 inputs, or you can use the single lookup table as 2 different lookup tables, each with 5 inputs. Really, we don't need 5 inputs. We need 3 input, and we need 2 of them with 3 input, one for the first row column, and the second one for the second column. So you only need a single lookup table to implement this particular truth table. What I'm trying to say in here, since there are no flip-flops, no clock, this is a purely combinational circuit in here. And ROM is useful whenever you want to store really long tables like these, like something that stores maybe thousands of lines or 50 lines or something like that, and you can generate them like automatically using some other programming languages, and for some reason or another you need that data in your design. Okay, but what if I really don't want to utilize the lookup tables because I have a system that is really large, and I really want to put all this data on the BRAM. Okay, so I'm going to show you now what we call a synchronous ROM. Okay, and synchronous ROM is my try to use BRAM as ROM, but as you might expect, the name BRAM specify it's RAM. It's actually not ROM, but we can hack our way through it, and we can consider it. It'll have to be a little bit different, and the reason why it's different is because it's synchronous now. ROM by nature shouldn't be synchronous. Typically, a ROM, a read-only memory, doesn't need a clock. It's not a sequential circuit. But because we want to use BRAM for it, and we're hacking our way through it, we need to actually put this input clock in here. So now we're adding a clock, we're adding an address, and we're adding a data. So technically, we're not adding the address and the data, we're just adding the clock in here. So let me show you how we can actually do that. It is very similar to the one with file in here. Let me just show you. I'm just going to copy that code and I'm just going to put it in here. Okay, so we're going to have to specify the ROM like we did before, and we're going to have to specify the initial so that we load it with some sort of value. Now this here should be different because it has to be, because it's synchronous, it has to be within an always block, and we're going to do it with a positive edge of the clock, and then you can do here beginning and end. Really now you have to do data equals, well, ROM address, and that actually just solves it. Okay, so now if you actually go and try to implement and write the report utilization or run the implementation, well, why don't I just do that and let's see what would happen. So it's interesting that the Rtl Analysis, the schematic, figured out that this is Rtl Rom, but because we have that particular clock and we're having the output to be synchronous, it just basically placed some sort of flip-flops or a register here at the output, and I'm assuming that register have the same size as the output, which is 2 bits, so you can see it's actually between 0 and 1, which is 2 bits. The implementation is being run, and as you can see, it finished the synthesis, and I'm taking a look at this table in here. I see that it's using one lookup table and one flip-flop. Interesting in here. Well, it's using this particular lookup table and flip-flops. It's not using any BRAM. So my hack to actually use BRAM has kind of failed. So this template is not working. So I'm going to have to work something else. And taking a look at the documentation, long documentations from Xilinx tells me the following. If you want to instruct Vivado to use BRAM as your memory, and it actually can, what you have to do is you have to give it what we call a synthesizer directive. And that synthesizer directive, I'm going to put it right before this here, okay? Right before the definition of, or the declaration of a memory between two different stars. So what you can say is, I want the ROM style to be equal to block. And if you do that, things will change. But that thing that changes is actually not the functionality of my synchronous ROM. So you can take a look at the Rtl analysis and you can see that it implemented it with an Rtl ROM followed by some sort of flip-flops. What will change is actually, if you take a look at the design runs, it's actually running the implementation, the synthesis, you're going to see that it will start using BRAM at this point. And fair enough, you can see that it stopped using lookup tables and flip-flops. It's now forced to use BRAM, and it's using half a BRAM because it's enough for it. Again, I want to re-emphasize that the only reason why we have synchronous ROM is because I want to utilize that BRAM in here. And the only way we can utilize BRAM is by using a clock and making it synchronous. But in reality, there is nothing called synchronous ROM. ROM is typically interpreted as a combinational circuit or just a large lookup table or something like that.